We are looking to enhance the Hungry Traveling Snake project from the WiByte Python curriculum available at www.wibyte.in. Recall, in our project, the snake is expected to eat all the food items and get back to the starting point. Clearly, the snake would want to do it in a good way, take a good path, one which is hopefully least number of steps. Now, in fact, this is an extremely important business problem, which is called the traveling salesman problem. This is important, for example, in logistics companies, in companies that are doing deliveries, and so on, because this directly impacts their, profitability. You can imagine that if a salesman is going around, has to visit multiple places, better that the salesman does that in an optimal way. I must warn you, however, that this discussion is quite involved, however, extremely, extremely interesting. So, my suggestion to you would be please go through it slowly in a step by step manner. Happy to discuss at all points because this is one of those, thoughts which can take your thinking to the next level. And I think that will be really useful to you as you go forward. Now, let's start with a very simple example. Let's say my snake had only three foods to eat, starting from here. Say I enable them 1, 2, 3, and let's say these are the distances between the fruits, between the, let's say, different foods. Now, clearly you might say, okay, look, I'm going to just list down all the paths that are there. For example, I could go 0 because 0 is where I start, 1, 2, 3 back to 0, or I could go 0, 1, 3, 2 back to 0, or I could go 0, 2, 1, 3 and back to 0, and so on. There are 6 possible ideas, but you'll realize very quickly that, well, in fact, 0, 1, 2, 3, 0 is same as 0, it is same as, in fact, 0, 3, 2, 1, 0, because notice this is just in the reverse direction. So the cost of these two will be exactly the same. In fact, it turns out that this also is the optimal path for this example. Now, let's just do a little bit of a variation. Let's say I add one more station to this, and that's what I've done. Now, these numbers are arbitrary. I just come up with this. But the point that I want to make is that with just 4 paths, with just one extra path added, the number of possibilities just goes up. In fact, you can show that this number of possibilities will go really, really fast. In this case, I could still somehow manually compute it by computing all the possible paths. It turns out that the optimal route is 0, 1, 4, 2, 3. But the point is clear that as the number of stations grows, the total number of paths grows very, very fast. In fact, you can show that this grows as a factorial. Factorial is basically n times n minus 1 times n minus 2 times n minus, let's say, 3 all the way until 1. So this goes really, really fast. For 10 stations or say 10 foods like we have in our snake game, there are more than 1.81 billion possibilities. Now, clearly, it's not possible for us to, compute each of these like the way we have done for those simple examples to find the best, because it's just way too much computation. And that's exactly the problem of traveling salesman, that it's a problem that grows in complexity very, very fast. For any practical size, it becomes extremely difficult to solve. Extremely, let's say, too many paths to be searched. Now, what that means, obviously, we don't give up here. What that means is that we have to think of some algorithms, think of some what we call heuristic algorithms, basically, like, which we think should be correct, and then probably tweak them to get, let's say, what is an optimal solution. Now, one such algorithm is called a greedy algorithm. It's actually nearest neighbor algorithm. Basically, the idea is that at all steps, I find the nearest next food and go there. Now, before I move forward, I mentioned here nearest neighbor and a greedy algorithm. Well, what is a greedy algorithm? Greedy algorithms are those that do the best at every step. So it looks quite, interesting, quite logical. But as you will find that they are not necessarily the best algorithms. In fact, quite, interestingly, quite surprisingly, we'll find that nearest neighbor will not necessarily give us the best route in this case. Let's take some examples. In the simple case of the 3 networks that we had, the same exact network here, it turns out, well, let's say I want to do the greedy algorithm. So I say, okay, starting from 1, which is the nearest node, which is the nearest food, let's say, well, that is 1. So I go to 1, that's fine. Now from 1, I go and find, I can go to either 2, I can go back to 3, I can go to 3, I won't go back to 1, obviously. So I say, look, between 2 and 3, I think 2 is good to go. So I go to 2. Now I must go to 3 because I've already gone to 1. I'm not going to go back here because I have to cover 3. So I say, well, I will go to, for example, 3. Now, once I do this, I come back to 1, and the optimal solution found then is basically the optimal path. So nearest neighbor, in fact, got us the optimal path. But let's take another example. The same example that I just showed you with 4, nodes. the nearest neighbor algorithm is in fact not optimal. Let's see this why. I mean, go through this. You will find that the nearest neighbor will take you to 10, to 20. So 1 to 2 to 3 to 4, and then back to 0. And the cost of this is 130 steps. Whereas if I were to somehow do an optimal route, it will be 1 to say 4, 2, 3, and back to 0. Now, this is very interesting. So the nearest neighbor is in fact not optimal, because it's what we call the greedy algorithm. And there's a parallel in general life as well. Sometimes we try to optimize only for the moment, but in that process, we lose track of the bigger picture. So kind of what's going on here. But really, though this is not optimal, this is in fact a very, very good programming practice to build this, because it creates a lot of intuition. And often you find that this is a starting point for more involved algorithms. It's not really not in our scope to kind of go deeper into, let's say, what is the most optimal algorithm here. That's a huge topic in itself. I urge you to, let's say, explore this. Now, if you are interested to explore, I'm more than willing to discuss. Look at the traveling salesman problem. There's plenty of resources on the internet. You can look at those. I'll be happy to discuss with you. But for now, we will stick with the nearest neighbor problem. We will try to solve the nearest neighbor problem using this kind of algorithm, and that's what I'm going to cover in this video. But then, think about it. Before we solve this, we need to store the X and Y locations of all the foods, because without that, nothing is possible. We're going to create a list called food pos, and the list items of this list will contain the XY positions of all the foods. And we will, in fact, update this as part of the food placement process. Using this, we can compute the distances between foods. Now, couple of points I'm going to make. For this purpose, we are going to ignore, in fact, disable the obstacles, poisons, etc. Because if you think about it, these change the distance between points because certain paths become unusable. So I've got to go, let's say, go around let's say, an obstacle and so on. We'll also disable the, the bonus where we said that, okay, you must eat in a certain order. We'll come back to this later, but for now we'll disable it. So keep it simple. So what we will do is that we'll just create a list called, let's say, food, food pos. Now, let this be an empty list to start with. So, the idea is that I'll just say list to hold food positions. Now, this is to start with an empty list. Now, I will keep appending to this the position of the food. I just go and say, well, in this list, food pos, so I say food, say, for example, pos dot append food dot say pos. Now, this is interesting because really what's going on is that in this list, I'm storing every food that is out there. Now, just for me to visualize where these turtles are being placed and what is a food pos list, I'm also adding a new turtle here called NN. Now, this is just kind of like a dummy turtle, which is going to write the index of the, the number of the turtle on the turtles. Let's see how this works. So when I, for example, so when I run this, notice I get 10 turtles being placed as before. 0th is here, 1, 2, 3, and so on and so forth. Now that's what the NN turtle does. Now let's say I just stop this and I look at, let's say, food pos list at this point of time. Now clearly food pos is a list, like I said. So if I were to see food pos 0, that's at 175.51. That's where I see my turtle 0. That's 0 here. So 175.51 sounds reasonable. So likewise, if I look at, let's say, turtle 9, well, 126 minus 63. So that's kind of from roughly here and this turtle. That makes sense. So notice that the list food position is now containing the XY coordinates of every food that we are placing. And this is very powerful. This is what we are going to work on. Now, notice here. So like I said, this list contains the XY position of every food item out there. Let's now understand what is our notion of distance. In fact, remember, our snake head only moves either horizontally or vertically. Basically, it can't go diagonally like this, which means that the distance between 2 points is not what is called the Euclidean distance, or let's say obtained by Pythagoras theorem. But here, very simply, the absolute distance between X coordinates and the Y coordinates. Now, for those of you who want to explore this further, this is called the Manhattan distance, and it has some interesting properties as well. But that's what we are looking at. So what do I mean by this? Well, if I have two food items, or let's say from 0, 0, and I want to find the distance between these points, well, all I need to do is to look at the absolute difference in the X coordinates and add to that the absolute distance between Y coordinates. and that's my distance. So how do I now, having done all this, how do I, let's say, proceed to find the, let's say, the nearest neighbor? Well, the idea is, remember, I start from 0, 0. What I'll do is that from 0, 0, I'll find distance to all the foods that are there. So there are 10 foods to start with, and I'll say, okay, let me pick the nearest food and I'll go to that food. Next, once I've gone to that food, I'll repeat this exercise. I'll the distance of all the foods except the foods that have already been eaten from this food. And I keep doing this till all the foods have been visited. Now, what I'm going, but before I get there, let me just kind of illustrate to you the idea in, so that it becomes easier to understand. I'm going to use multiple lists for this purpose. We already have the list of foods. We already have this list called food position. Now these two will be my golden lists. I'm not going to disturb them because we use them for a lot of things later as well. Now, I'm going to create a temporary list called foods, which is just going to be a copy of, let's say, list of foods to start with. I'm going to create two more lists, order and distance vector, which are to start with, let's say, empty. Like I said, start from 0, 0. I know from 0, 0, all these points, what are the distance from each of these? I will find the nearest of them. So, like I said, start from 0, 0. I need to find the nearest food item from 0, 0. So what I will do is that I'll find out the distance from 0, 0 to food 0, food 1, food 2, food 3, and so on and so forth. And I'll pick up the minimum of all that. Let's say that happens to be food 3. The moment that happens, I'm going to say, okay, in my list called order, I will put 3 because that's where I must go first. I will delete 3 from this list because I don't want to be searching this list anymore. And in this distance vector, I'll put the distance, which is D3 to origin, because I know that is the smallest distance amongst all these distances. So 3 is the nearest one, and hence I put that, and we update the lists. Next step, let's say I will compute the distance from 3. So I know food 3 was the minimum distance. I am going to find out the distance between all these foods from 3 to all these foods. Let's say that happens to be, let's say, food number 1. I will say, oh, all right. So I'm going to put 1 in the next in the order, and what I'll put here is the distance from 3 to 1. I will remove 3 from the food. So this will ensure that if I'm iterating through the foods, I will never repeat a food. And remember, the end goal of this is to come back to 0, 0. So that's kind of guaranteed here because I'll just go through, find the nearest food all the time. At the end of this algo, I will end up in a situation where, well, my list of foods and food pause will remain as they were. My foods list will be empty. My order will contain the optimal order, or say the nearest neighbor order that I must go. So for example, in this case, perhaps 3, 1, 2, 4. I just randomly put these numbers just to illustrate. My distance vector will contain distance to 3 from 0, 0, distance between 3 and 1, between, let's say, 1 and 2, between 2 and 4, between 4 and 0, node number 0. And of course, from here, I have to come back to 0, 0. So basically, distance vector contains the distance to each of the nearest neighbors. So coming to the code of this now, like I said, I'm going to do this in a while loop, go through this slowly. It's quite logical. I'll try to explain every piece of this in, let's say, at a high level, and then we'll implement this in code. The whole idea is that I'll create a function to compute distance between any two positions, xy coordinates. Remember, all I need to do is to find out the difference between the absolute difference between the x coordinates, which is the zeroth point of this, and the absolute version of the y coordinates, and add them. That's the Manhattan distance. Now, what I'm doing here is, like I said, I create a list called foods, which is exactly same as list of foods because that goes from 0 until 9. That's what this statement does. Now, I keep doing this while the list is, still has elements. So what I do is that I find distance to every item in foods from the present item. Now, remember, when I start this algorithm, present is 0, 0. So I find the distance from every food item to the present position. And I want to find the minimum of all that. So how do I find the minimum? Well, I just say, okay, look, if my distance is smaller than the previous minimum distance, then this must be the minimum distance. Now, this is quite interesting. To start with, I initialize dmin to a very, very, very large number. Now, this may look strange. This may look strange, but the idea is that the dmin initialization is so large that even the first distance, however large it is, will be less than this. And that way, I'll ensure that I'll always pick the minimum distance. Now, having done this minimum distance, I will find out, where is the minimum kk, which is my kk min, because every time I update kk min, so I keep going to the lowest distance. I will say, okay, that's my new present food. I will append that to my order. I will append the distance, the dmin, to my distance vector, like we discussed. I will very, very importantly remove this from the foods because I don't want to retain this anymore, and I'll again reset my daemon because next food, when I start looking at the other foods from the present food, again the same thing should happen. I must make sure that the food is picks up the minimum very nicely. Now think about this. Happy to discuss it. Now we will implement this in code and see it working. But before I go there, I just want to give you an example so that you have a feel of where we are going. This is one placement that I had done before this video. Notice here 07194562238 is the order that my algorithm picks up by just going to the minimum distance and the nearest neighbor. And this kind of sounds logical. From zero, this is from 00. This looks the closest, clearly to so. From here, this looks the closest. 7. From here, it could be this or this, but let's believe the algorithm. And I kind of trust that because, the Y position is X position almost the same. So this has to be the closest. From here, this and so on. So you notice that the algorithm indeed finds you the minimum distance, the nearest neighbor, and it looks pretty cool. All right. So as I said, I'm going to define a function here called, say, distance. Now this gives me the Manhattan distance between two positions. So I just call them pos, let's say, final, and pos, say, initial. Let's just put a comment as a matter of good habit. Manhattan distance between the two x y coordinates. And like I said, this is nothing but, well, I'm just going to return from this function. I'm going to just return from this function, let's say, abs value of, so I have to be a little bit careful here, pos final, let's say, 0 minus pos initial, say, 0, because remember the absolute value of x difference plus the absolute value of the y difference. So I just go and say abs of, let's say, pos final. Now be careful on this because this can cause errors, of 1 and minus pos initial of, say, 1. Now this will be the Manhattan distance between those 2 points, because remember final and initial are both tuples. Both are basically xy coordinates. So I'm looking at the 0th element, the x coordinate. I'm adding to that the first element, that is the y coordinate. Let's say a list called, so let's say I just call it n nearest neighbor order, which is equivalent to my order list here. So I just call it, let's say, n order is an empty list. Dist vector is also an empty vector. So this, let's say, vec is also an empty list. My present is to start from, say, 0, 0, 0. My d min, now this is interesting. I'll make it quite large. Again, like I said, happy to discuss, but think through this. Just want to make sure that the first, I just want to make sure that the first distance itself is smaller than this. So I just make it very, very large. With more 0, it won't hurt. And then basically I just say, okay, look, kk min is 0 because that's where I want to start. So kk min is equal to 0. And I'm going to create a list called foods, which is exactly same as the list of foods. So I just say x for x in range, let's say 10. Now again, I'm happy to discuss with you. Think through this. Why did I not do foods is equal to list of foods? That's actually quite an interesting point. But I just define it again. The values are exactly the same, as you can imagine. Now I'm going to do this while my length of foods is greater than 0. So I set up a while loop. So I say while, well, length of, say, foods is, for example, greater than 0. While this happens, well, for kk in foods, so I just look through this list. This list kk in foods, I just compute, say, d is, say, distance between, let's say, food pos kk and present, because remember these are the xy positions of the food that I'm looking at. So I just go through every position in this list. I go to the go to the food position and find the distance between the present and that point, and I just say, well, if, say, d is less than d, say, min, then I will if the d is less than equal to d min, then I'm just going to update my d min and my kk min to be equal to, say, d and kk. Now this is also an interesting Python syntax. I can assign, I don't need two statements to assign this. I just say, okay, d min kk min is equal to d and kk. So d min will become equal to d, kk min will become equal to kk. It's quite interesting actually if you use it this way. Now having done this, I'm going to so I run my for loop through this. My present will then be nothing but the food pos, let's say kk min, because that's the minimum food, that's the like the least distance that I found from the previous position. Now, having done this, I'm going to append my nn order dot append, kk min, because this must go into the list nearest neighbor order. I'm going to say, well, dist vec dot say append say d min. Now, having done this, clearly I must remove these from the list foods here. So I just say foods dot remove, in this case, I just go and remove kk min because that food has been found. I don't need to go back to that food again. And finally, because this iteration is over, my next present value has been set. Again, I must set d min to, let's say, a large number here. Just go with the same one here. I think I set it to 1 billion, and I'll do the same thing. And with this, we can, I think I can just put like a comment here. Nearest neighbor neighbor route, let's say. Once this loop is over, I come and say, well, print for me please the n and order, so I can see what it's picked up, and print also for me, let's say, the dist say vec. Yeah, so that I can look at these quantities. Now, if you want, and I urge you to, when you're developing this, put some prints inside these so that you can understand the dynamics of this. Very interesting, but I'm keeping it kind of brief here because in the interest of time. Now, when I run this order that I have been, let's say, chosen from the nearest neighbor algorithm is 0, 2. So I basically say, well, I start from here. I go to 0. I go to then 2. Then it says go to 3. Well, go to 4. Sounds quite logical. Go to 9. Go to 5. Go to 8. Go to 6. Well, from here, there's a large distance because I got to bite the bullet. So I go to 7. I go to 1, and then from here I can come back. Now, sounds quite logical, whatever this algorithm is done. Just to be sort of doubly sure, what we can do is we can look at, for example, the food pos, let's say 0, because that's where this guy is asking us to go, and that is indeed quite small compared to, let's say, food pos, 2. That, so notice that food pos 0 is, so those 0 and 2 look like close enough, but in fact 0 is closer, so that's where I have gone. And it looks to me that the algorithm has done a fairly good job here, right? Now, how do I determine the total number of steps that the snake must take to complete this entire course? Well, the idea is already there. Remember, the distance vector, or say I call it d vector over here, it contains the distance the snake would need to travel to each of the next neighbor. So we can just keep adding up all these items on this list d vector. And finally, to add to this, we must remember add the distance from the last item of the order to 0, 0, because then the snake must come back to 0, 0. So this, will be the total number of steps, and I can do that quite easily in code. Let me just do that very quickly. So I just go and say, well, look, the optimal distance given this. So I just go and say, well, so I come to my code here. Let me just put a comment here, say distance, for the, let's say, nearest neighbor route. Well, I can just say, well, let's call it opt distance, though it, like I said, it may not be optimal, but never mind. So we just call it, say, opt distance, set it to 0 to start with. I say, well, for, let's say, d in, say, dist vector, so distance vector, I say opt distance is, so basically this is like summing up all the values. Now to this, I must add the distance that it takes to come back from the last order to, say, 0, 0. So I just say plus equals to dist food pos, say, order, actually it has to be nn order, and -1. So that's the last item. And coming back to, let's say, say 0, 0. Now be be very clear about what's going on with the indexing here. I'm indexing in two steps. So this is the last item of the NN order because that's where the snake is last sort of recommended to go last. And I'm looking at the position of that. So that's double indexing going on over here, right? And let's find the distance between these. Now, having computed the optimal distance, the nearest neighbor distance, perhaps may not optimal, we can use it still because remember at the end of the game, we are putting the steps that it has taken us to complete this. I'm just going to use this piece of code again. So I just come here and I say, well, look, copy this piece of code. And this time write for me what would have been the optimal steps. Say OPT steps. Now, even though, like I said, it may not be optimal, but very likely it's way smaller than the steps we have taken. And this time round, I just need to say, well, string, let's say, so I just say opt, say distance. And note, I do not need to multiply by 20 because this opt distance is already in pixels. Remember, the reason we are multiplying steps with 20 was because we want to convert from steps to pixels, but this opt distance is already in pixels. So I don't have to do anything. However, in order to make sure that these two do not go on top of each other, I just go and say, well, report, let's say report dot go to, for example, 0 and say minus 100, right? Just a bit of a displacement between these two. And, before I run this, in order to keep my screen not cluttered, I'm going to also remove those number markings that, previously we were using. So I just go and say, look, let me just comment out, let's say this piece of the code. When I run this now, let me just try to, let's say, eat these fruits, what I think could be a reasonably optimal way. So I'm doing this. It looks like I'm not doing too much of circuits here. So I eat this one, there's one more to go, and then after that I come back to the center. I come back and I think I've been fairly optimal with my placements, and indeed I see that. So I took say around 1980 steps, but optimal would have been 1560. We'll take one more example. This time I'll deliberately go, let's say, in a very circuitous route to see if my optimal could have been better. Let's say I deliberately do a bad job here trying to go sort of across the whole field all the time before catching the fruits. I would think that my optimal will be way different from what I'm sort of achieving here. So let's say I go back and catch that. Now this is clearly an optimal. Sometimes it's very easy to recognize not a very good route, which is what I'm doing here. Now let's say I go here and I come back to the center. Clearly this route doesn't look very optimal to me. Oops, again missed the center. So let's see, I try to go back to the center. I do this and notice there's a big difference between what would have been optimal and what I'm doing. And that's just quite interesting. I hope this has been interesting to you. Clearly, this is quite involved, but go in a step-by-step manner. I'm happy to discuss with you at any point. In general, if you think learning like this through activities is something that you enjoy, look at our website because that's how we learn Python programming. Take care. Thank you so much. Enjoy programming.